Welcome everyone, and thanks for tuning in to this presentation on timber portal frames. For those of you who don't know me, I'm the Principal Engineer for Meyer Timber in New South Wales. Meyer Timber is one of the largest distributors of timber products in Australia and supplies both merchants and the Frame and Truss Centre with timber and associated products. Afzal Lafi, my colleague in Victoria, and I provide high-level technical expertise to our customer base and look for new solutions to fill gaps in the construction process. Why start my presentation with commercial buildings? These are examples of what you commonly think of when timber portal frames are mentioned. Rob will focus on this sector, but you can see the Meyer Timber New South Wales warehouse and two projects from New Zealand, being the Carter Holt Harvey Dry Mill and the Museum of Technology and Transport Aviation Hall. They involve large volumes of timber and require a level of expertise for optimise and erection, but they're cost comparable to steel and provide positive psychological and physiological environments. I personally go through our warehouse every day I'm in the office, and although I may have some bias, I find it a warmer and more soothing space. But why limit our view of timber portals to large commercial structures? The alternative is detached single-family dwellings or multi-row townhouses. In Australia, these are predominantly lightweight timber frames. The timber used is either individually designed, things like floor joists and wall studs, or through a system solution like nail-plated roof trusses. So is there a market for timber portal frames in the family home? Timber portal frames can sometimes replace steel, and builders prefer a one-stop shop for the primary structure, as it can create issues when steel and timber are fabricated and supplied separately. Residential housing is also a simple path to market. Commercial buildings often go through one or more complex tender processes which take a long time. In comparison, a residential home is commonly quoted and ordered in timescales of weeks rather than months. And even though volumes may be low on an individual project, the high quantity makes it a viable proposition. But where can we see timber portals being used in homes? Around an opening to create a bracing unit, replacing steel in large open plan living areas, or even an alternative for the rural shed market. We'll explore a couple of these in the presentation today. Let's firstly consider wall bracing. The progression of architecture in Australia has been to create homes with large open plan living, along with taller walls and larger windows. These factors mean there are fewer walls capable of resisting wind loads, and the higher walls actually increase the racking forces. It's a tug of war between the architect and the designer of the building, and coming up with compliant bracing is the challenge. AS 1684 is the residential timber framing standard, which sets out requirements for quantity and distribution of bracing units, but in many cases, like in the picture shown, it's very difficult to meet these requirements. How do we tackle this dilemma? Essentially, solid walls that are longer than 600 millimetres can be braced with sheet bracing like OSB, ply or hardboard, or with metal strap bracing. Once you get narrower than 600, the capacities drop off significantly and these solutions become unviable. Nail plate companies have developed a variety of narrow timber truss braces which give better capacities, and there are also steel truss brace solutions. The issues with these are twofold in terms of tie down and cost. For a short wall brace, which is 2400 high and only 400 wide, simple mechanics show you that the tie down force is 6 times the racking load at the top. So a 5 kilonewton racking force needs a 30 kilonewton tie down, which means chemical anchoring to the slab. And the cost should actually combine the unit cost as well as the installation cost, which is higher with chemical anchoring. Added to this, the steel truss braces remove the one-stop shop scenario for the builder, whilst making it harder for follow-on trades like electricians and plasterers. So why can't we utilise a timber portal frame around openings, where the cost, tie-down requirement and installation are all reasonable? One such off-the-shelf product available in Australia is the Simpson Strongtype PFS or portal frame system. This uses double LVL columns and beams in conjunction with a portal frame accessory kit. It's suitable for openings from 600mm to 5.5 metres wide and a maximum height of 3 metres. For this range, there is a single capacity as shown in the table, So essentially you have a single product to fit all conditions. If you have 300 millimetres on one side and on either side of the opening, you get a racking capacity of 5.87 kilonewtons. If you have 300 millimetres on one side and only 90 millimetres on the other, it becomes a single wall portal with a 2.94 kilonewton capacity. The accessory kit comes with all the hardware to construct the portal frame, but the LVL pieces and anchorage items need to be bought separately. It should be noted that the tie down of the Simpson portal frame system is still through chemical anchoring. It requires 16mm threaded rod epoxy set into the concrete, and a 400 deep edge beam is needed in the areas of tie down. To further simplify portal frame bracing, we've developed a product called Mybrace. It uses prefabricated composite sections, which are essentially C-section columns and lintel with the LVL pieces overlapping in the corners. Here, a moment connection is provided with screws, which are located into pre-drilled holes in the columns. You just need to ensure the column and lintel are tight against each other, then fill up all the holes with screws. With a moment connection in the corners, the anchorage to slab is significantly less, so we utilise concrete screw bolts that are common in residential construction. The kit comes complete with all the items needed: columns, lintel, moment screws, tie-down bracket and screw bolts, as shown in the picture in the centre, so nothing else is needed. In using mechanical anchors, it means that the bracing unit can either be assembled on site or can even be built into a manufactured wall frame in the factory. Also, by designing and making to the exact opening, we have the ability to change the column and lintel sizes to suit. Normally the columns are the same width, so a designation of Mybrace 3036 has 300 wide columns and a 360 deep lintel. But what capacities does a solution like this have? The capacity depends on the opening size and loads on the lintel. Looking at the tables, which are included in the Mybrace technical flyer, a Mybrace 3030, being 300 columns and lintel, can have a capacity in a non-load bearing wall of up to 7.1 kilonewtons. It can also get a racking load of up to 6 kilonewtons in a load bearing wall scenario. This will in most cases be enough to deal with even distribution. It has a simple mechanical tie down and comes out cheaper in cost than a steel truss brace system. Mybrace can also be used in multi-storey buildings, carrying both roof and floor loads. To do a bespoke solution for every individual opening requires a level of automation. And this is where I have to give credit to Afsal, who developed the Mybrace system with me. An order request comes from the customer with all the information needed for the design of a standard Mybrace. We can then use our internal design tool to quickly check and size the timber members. Note that with all timber portal systems, the lintel design is included as part of the brace, meaning the bracing unit also resists gravity loads. The design tool calculations include lintel design, column design, sway deflection, knee joint moment capacity and tie down. Once the customer approves the proposal and orders the Mybrace, the design tool automatically calculates a BVX file for all the components, including the drilling of the screw pattern, which is sent to a Humdegger saw to be precision cut. The composite sections are fabricated, ancillaries included, and the unit packaged up and sent to the customer. This process can take as little as 2 days from order. After delivery, the final piece of the puzzle is the installation guide with step-by-step instructions on how to construct the Mybrace. So let's look at some examples. On the left is a very common scenario: a 3 metre wide garage that has a 2.4 metre door in it, leaving only 300 mm on either side. A Mybrace 3030 here allowed the wall to be braced with 5.3 kilonewtons of racking capacity, but it also provides a stiff wall in which to mount the roller door. On the right is a similar situation with a pool cabana extension. You can note in this case, the columns are cantilevered to the top of the wall frame so that they can take the racking loads from the ceiling diaphragm back down to the portal frame. Mybrace can also encompass multiple openings. On the left, we have a Mybrace 3630 over the top of a combination window. The lintel here is designed to span the whole length, meaning the inside of the opening is only infill framing. The 360 columns allow for a stronger knee joint connection to give a stiffer portal frame. If you look at those last three examples, the assembly time of each of them was in the order of 20 minutes, which makes it a quick and easy process. Then on the right, we have what's called a special Mybrace. This is a stacker door opening out onto a deck with ocean views, which happens in many coastal villages in Australia. The design was done from scratch as the internal design tool does not cater for this complexity yet. It has 300 wide composite columns, a 240 deep raked composite lintel, and a double 300 deep LVL at the top of the stacker door, which also acts as a wind beam. The combination of the double horizontal members made for a stiff frame unit with 6.2 kilonewtons racking capacity. In this instance, it was tied down to a timber floor, so the tie-down bracket was the same, but 18 gauge washer head frame screws were used for tie-down instead of screw bolts. Timber portal frame bracing systems are going to become more prevalent in residential construction. There are currently the two systems discussed here, but I'm sure there's others in development. Now, if we look at some other domestic portal frame opportunities, I'll touch on two case studies. The first is a combined house, shed and workshop in Tasmania. The architect mentioned to the builder that the timber portals could be done as truss portals. Once the frame and truss company was contacted, they recommended solid timber portals as shown in a previous project at the bottom right of screen. This span is perfect for a timber portal scenario and it crosses over a bit into the rural shed market. You can see the large workshop at one end that is essentially a 9-metre span by 22-metre long shed. If we design all the portals the same, there's no reliance on the internal bracing walls and it makes supply and assembly easier. For this proposal, the wind classification was taken as N3 as the exact location was not provided, and this is common for rural shed style buildings. A 4-metre base spacing gave a design of 190 by 45 LVL purlins at 900 centres, which butt into the timber portals. This is different to steel portal designs where CZ or top hat sections continue over the top of the portals. As the timber purlins are deeper than steel purlins, by butting them into the side, it maximises the head height available, but also provides lateral restraint to the rafter element of the portal. From a cursory look at the loadings, there were 4 load cases considered in the preliminary design. These were dead and wind load combinations for strength, and then serviceability wind loads for sway design. 2 options have been proposed with slightly different member sizes. To keep column section width down and maximise available clear width in the workshop, the column was designed as a box beam. This allows the solid LVL sides to continue up and a single rafter to slip in between them. The gusset connection at the knee then only requires a screw pattern to be designed. As the rafters are single members, there will have to be a plywood gusset required at the apex to join them together. You can see that double 360 by 45 LVL box beam columns with a 450 by 63 rafter has given the most cost-effective option, and it's around half of what a structural steel solution would cost. You need to be wary when comparing a design such as this to a rural shed in terms of the cost and also the member sizes, as rural shed loadings are not as severe and allowable serviceability deflections are higher, with them being Class 10 buildings. This proposal is currently under review with the architect and owner. The second case study is a single family home in New South Wales, which has an open plan vaulted living area in the centre of it. We were initially asked to do the subfloor design through our detailing department. And in reviewing the plans, it was noted that the current design included a lot of structural steel in the open plan living. Going back to the frame and truss company, we asked if they would be interested in a potential timber framed option to replace the steel, and this led to us putting forward an alternative timber option. If you look at the plan view, there are a number of points which help to achieve an integrated and more cost-effective timber design. The portal frames are located along the orange coloured horizontal grid lines shown on the plan, and the 2 central ones have lengths of wall continuing on both sides. These walls will provide sway resistance to the portal frames and essentially turn them into gravity frames. The section view also shows that the central area in the portal direction is predominantly protected by the rest of the structure. So very little wind load is applied directly to the vaulted area. So our proposal was as follows. PF1 were the 2 central gravity portals, which have lateral supports from the adjacent bracing walls. PF2 is a small portal across the front entry, where the columns are restrained out of plane by a lowered flat front porch roof. PF3 is across the rear of the house, with some restraint from the masonry fireplace wall. And PF4 at the end of the alfresco remains as steel. This is from an architectural perspective, as the columns need to fit inside the box brick piers. We don't truly get a one-stop solution with this, but very close to it. It's important to remember here that timber can't do everything. Sometimes you need to use other materials. As an eminent engineer said a few years ago, you don't need to design the best timber building, you need to design the best building and use the right materials, including timber, where they are best suited. So looking at the portals, a combination of members has been chosen for this project. The columns are a prefabricated C-section, the same as the Mybrace system. This allows them to be hidden inside the 90mm wall widths on each side. The rafters are 45mm LVL on either side of the column LVL extension. If you reverse the orientation of the opposing column, then the apex just becomes a double 45mm LVL which overlaps. The double LVL rafters also provided an additional shear plane for the screws, which increases the design capacity. The bottom line here is that the cost of the timber option will be thousands of dollars less than the structural steel option, and it will connect a lot easier to the lightweight timber walls. This project is about to get underway in a month or so, and I'm pretty confident that the timber option will be chosen. So timber portals are not just suitable for large-scale industrial and commercial buildings. And from this brief presentation, there are many instances where timber can be used and is most cost-effective option in the residential sector. It's about recognising what's possible and approaching your engineer or one of the engineered wood products distributors and asking the question. But if you want to use timber portals in large span application, then I'll hand it over to Rob to let you know how this can be done. Thank you.
All right. Thank you, Andrew and George. Thank you for your presentation, George. Very good to see that we have a domestic use of portal frames. There's always been a lack in the market on an alternative solution to steel. It's good to see we've got some systems through there. Thank you, everybody, for turning up and attending today's lecture. My name is Robert Nestic. I'm a senior structural design engineer with TJ Engineers. We are a multi-discipline practice, not only timber, we design steel, concrete and all the other types of materials as well, but we have a specialty focus on large timber buildings. Large timber portal frames is a specialty of mine, and I've been doing them for about 30 years now and coming up with systems that are viable and economical to compete against traditional steel, not only in the decorative market or the architectural market, but also in the industrial market as well. So today's presentation, we'll go through briefly through some elements in the types of building environments that timber portal frames are used in, the geometric forms that are capable of timber frames. We'll look at some structural sections, what's commonly available and most economical to use in some of these items or these buildings. We'll look at some design aspects. We won't go into too much detail in design, but just highlight some of the things that need to be considered during portal frame design. And we'll look at some construction aspects as well. Definitely with timber, there's some challenging things on site that we need to take into account, and we'll go through those as well. Also talk about some secondary framing, purlins and girts and mullions, and what's most applicable for those applications. And we'll go through the case study of the Meyer Timber building. Portal frames are an ideal way to achieve large open spans and also have areas where we can provide an activity without impedance on the structure. They're ideal from two aspects. They can carry the vertical dead loads, but also take out the horizontal wind loads that may be applied to it. So they're a very efficient system from that point of view. Just briefly, we'll go through some designs and some aspects where they can be used. Domestically, they can be used in housing, as you can see in the top left and the bottom right, and they become quite ornate and also provide a function to the building. Industrial buildings we'll look at. Commercially, the top right is a office building in Brisbane, 2-storey. We have a 12-metre clear span on the underside and a 12-metre clear span on the roof, the first level, and we have 4-metre bays in there. That was all prefabbed structure and erected in Brisbane. Bottom left, we have a portal frame system that was converted into a barn, a rural barn, but a residential structure within that system as well. They can be used in large sporting arenas. So the top left is the Netball Centre in Sydney. The right-hand side is a structure in Mount Gambier. It has a timber gantry rail system, so it's got the ability to support, I think, maybe a 10-tonne gantry crane through there. It's 10 metres high. It was one of the first large portal frames in Australia to be built back in the 80s. Bottom left-hand side, we have a school hall, which is made out of glulam and has some steel bracing and other elements through there to provide the clear span. We can also use them in curved glulams as the top two to provide a geometric shape that's more pleasing. And portal frames don't necessarily have to be just straight elements, as you see in the bottom left. We can become creative and come up with other options that provide a more pleasing view. They're good for swimming pools because they resist corrosion. So with the right mix of fasteners, so stainless steel connectors, the timber in that environment is inert to the chemicals such as chlorine or salt and provides a good option for those kind of environments. Also in the top left is a composting shed. So that was designed back in the early 90s in Mildura. The client there used a steel shed and because of the high ammonia release from the composting, steel purlins had corroded within a year. This shed was designed with a 30-metre span and at 6 metre high at the eaves. All the elements were either hot dip galvanised, all the structural elements, or stainless steel fixings and screws. That shed has had no issue for the last 30-odd years through there, so that provides a very inert environment for the structure. As you can see on the top right, we have an industrial shed, so used for just factory type activities, but also we have a public library on the bottom one, which with some curves cut into the alveole provides a very attractive structure. Basically, portal frames can be provided as a skillion system, straight beams or a gable. We can have curved elements and a curved knee or haunch at the base to provide a connection-free section through there, or we can provide an arch type structure with a collar tie, and in some instances that's needed to be used. As you can see, within Australia, we have the capability of making some of these curved elements. So there are a number of glulam suppliers who can provide that type of system available. You need to contact those providers and to find out the costings involved. Otherwise, we could do it out of segmented other sections of alveole or glulam. What's commonly available within Australia in terms of materials for portal frames. In solid sections, we have glulam available in radiata pine generally, or a number of other pine products, GL13, but also in GL18 hardwoods and GL17 hardwood. So they're commonly available, and up to As far as I'm aware, they're up to 1400 in depth and 450 in width. So there's some of the large sections are available now within Australia. LVL is made within Australia, so we have the ability to purchase material locally, and generally the billets are 1200 wide and come in various thicknesses generally up to 75 mm in thickness. Both of the materials, LVL is available in 13.6 and with special orders available in longer length. Glulam is made to order. It just depends on the capacity of the place. So generally, you get some fairly large sizes. Generally, what we find in large industrial warehouses that the box beam system are most effective and cost-effective means of providing sections. So you can see in that lower diagram, we have a LVL box beam which uses LVL sheets as the webs, and within that web we have what we call cross-banded. So not only do not all the fibre is running longitudinally, a number of the veneers are turned perpendicular to provide stability to the timber. So during its lifespan, it doesn't shrink and swell, and provides the ability to screw and place fixings at regular centres. An alternative to the web is a plywood web. So within Australia, we have a number of plywood manufacturers who provide up to 50 mm thick in 1200 deep sheets of ply. So we could do it as a plywood box beam if we wish. And generally the flanges are sawn timber or LVL. Glulam can be used if it's a decorative situation, but generally the cost is the issue there. So on the bottom right-hand corner, you can see there a typical box beam type section of LVL. You can see the distinct flanges and webs, and they were glued and screwed or glued and nailed together in the process. I've provided this table, which will provide just rough sizing. It's not I wouldn't take it as gospel, but it depends on the locality and what kind of roof loads. But just generally for a lightweight roof shed, so 10 to 15 kilograms, no lining. These are the types of member sizes that you would generally adopt for the different types of spans and spacings. So as you can see in the 10 metre, 6 metre bay application, we're looking around the 420 to the 470 mark, depending on which product we're using. And a slight increase when we go 8 metre bays. But a 20 metre span portal frame, 675 LVL or the alternatives in Glulam are available, 8 metre bays through there. Generally, we find in large timber portal frame type applications, the wider the bay we can make it, for 8, 10 metres, etc., or even greater, depending on the structure, will provide a more cost-effective solution to the structure. 40 metres clear spans, so single clear span, 1200 deep box beams, those kind of sizes are needed, and glulams of similar depth as well would be required to do those things. At a 10 metre bay, 40 metre span, we would look at a box beam with a knee brace type structure to provide the ability to stand that distance. So typically on the left, on anything larger than 40 metres or larger than 30 metres, we try, so if you're looking at a 60 metre wide structure, we look at it providing an internal prop column type system. And that allows us to then get away with solid sections. So the more fabrication that's required to make box beams, etc., the cost is higher. So therefore we want to maximise our use on those. We push the portals further apart. But in cases where we can use solid sections, such as LVL or Glulam, the introduction of a column will enable us to use solid sections, which reduces the cost of fabrication. Plywood box beam portal is the one on the right. That there, 800 deep section, 12 metre span, 7 metres high, has an unusual cranked shape as part of the form, and it had to match a particular type of timber internal of the main building beside it, a very light wood colour, and so we provided a design for a structure of a box beam and then on the external face they glued a B-grade veneer ply, radiator ply, which then gave it the seamless look of a solid timber, and there was significant cost savings in doing a box beam in the form. Design, generally AS 1720 is a very good design code when you compare it to design codes around the different precincts, especially Europe and America. We did a lot of research in the early days back in the 60s, and a lot of the data that's in there is relevant today still in terms of fixings. We have a degree of confidence in those designs and fixing data, but also built in some, some conservatism in terms of the movement of the joints. Our values that are published in there already cater for the movement or the embedment within the joints. So you need to take that into account. But generally, dead load deflection is the governing criteria for deflection of beams or deflection of portal frames. So that needs to be considered and designed for. With portal frames, we can use camber to reduce the dead load deflection effects. So with such large portal frames, we are able to pre-camber up the elements in the glulam by having them curved. If we're doing box beams, we then pitch the ridge up higher than we would normally and bring the columns in to cater for the dead load deflection. So it shouldn't become the governing factor in most instances, but it should be able to be designed out. So sometimes we see very large member sizes, and that's because of dead load deflection, but we can reduce the member size and make it strength dependent generally if we put some pre-camber. Joint stiffness needs to be taken into account. We find that the joint rotation, a knee joint or an apex joint, can add, in the dead load deflection case, about 10 to 20% rotation. You tend to find that small fasteners, screws and code screws and dowels will provide a stiffer joint than a small number of bolts in the joint. But that's not to say you can't use bolts. It's just a matter of making sure that that's catered for in the design. And then with bolts, normally you have a slightly oversized hole, so you need to take into account that slip that may occur. Where screws, self-drilling screws, are a tight fit, so there's no initial slip, but you do get some embedment, but you get additional joint rotation. Appendix E is a very underutilised area of our timber code, and it has a high degree of, it gives us the ability to design members in portal frames with some other benefits and taking into account the actual material properties. The section 3 of the code is very conservative. It's based on a constant moment diagram, whereas if you go to Appendix E, you can take into account the bending moment shape and the lateral support locations. You can take into account having lateral supports on the tension edge rather than the compression edge when you're looking at members. And there's generally a benefit in going into Appendix E for rafters and column design as well. Sometimes we use partial fixed bases. So because we have such large members attaching to the base connection or base plate, we find that we can take some degree of fixity at the base. And that's generally, I adopt that only in lateral cases, so lateral wing, as it is a short-term load, but where we have long-term loads, I tend to think it's a base. Connections, multitude of types of connections and cost dependent. External gussets, generally, whether they're steel or plywood, is going to be the most economical, not the most pretty, but they provide the most economical design and also provide the best outcome. Slotted places, the bottom right-hand corner, we have some bolts. We have a member that's slotted for a 10mm steel plate, so that provides a reasonable connection through there, and you still see the fasteners. Pin and groove, so you can also, similar to what George had in his presentation, we have 3 elements of LVL glued up as the column, and the centerpiece extends up, and then we also have 3 elements for the rafter, and the centerpiece is short at the end so that we can overlap them and screw them together. That's a very cost effective and easy to install system. You can then go to some prefabricated bracketry that's exposed or hidden within elements, and that becomes quite expensive, but may perform and provide a different aesthetic to the structure. There are some other types of connection details. So the bottom photo is a Mybrace system. So that's very economical. May not be the most attractive, but it has its function in certain structures. You have proprietary systems. That's the one in the top left, which is from Xpan in New Zealand and Australia. A joint effort there to develop that system, which is a very simple bolted connection on site, but are glued and screwed plates that are attached to each of the elements. Or you go for a prefabricated horn system as the top right. Base plates can be fairly basic. An external bracket attached to the external part of the column, or a hidden base bracket with connections concealed, or a plated system or fin plate that's then welded to the casting plate on the slab. So we don't have any visible base bracket. Construction, generally fine. Yet construction can be an issue, especially in high rain periods or very high heat periods. So timber is a product or material that moves when it's wet or dry. So we try to minimise the exposure to the elements. Unfortunately, the picture on the right shows one of our systems not well protected after it was installed. So they're basically recladding that so that it's protected. But we suggest a protective wrap across all elements, protective paint coatings, impact protection. So you just got to make sure that at low levels you may need to put a false piece of plywood or board on there, just protect it while it's during construction phase. And the use of soft slings for lifting, not chain. That's most riggers we like to use. Avoid wetting from rain, so beams and joints swell. When we've got large sections of timber that are 1,200 deep, that moisture uptake can cause some large movements, and we don't want to put added stress on our joints. So it's important to keep them as dry as possible, and also to avoid cheds and splits during drying phase, during summer. Secondary framing, generally, if it's under 6 metres, we can use sawn timber, LVL or glulam, depending on its appearance. As you can see, the top element there is an I-beam, so you can also use I-beams as well in these kinds of structures. 6 to 8 metres, solid sections, LVL and glulam, and I-beams. Greater than 8 metres, I-beams are more suitable, and we do have a good range of I-beams available, up to 450 in depth from a number of our suppliers, but also make box beams as well. So as you'll see in the case study on the Meyer Timber, we used box beam purlins, and the reason there was we had to span 15 metres for our purlins, so that's partly the reason we used them there. So next we'll go on to the case study, Meyer Timber, Penrith, New South Wales, 22,000 square metre warehouse, largest timber. I'm going to claim this. It's the largest timber frame in the Southern Hemisphere. Taking into account the office building, I believe it's the largest timber warehouse in the Southern Hemisphere. We have 2 29-metre spans each side with a centre span of 32, as you can see, and a canopy of 9 metres through there. So a fairly large open plan structure through there. The main frames were 1,200 deep box beams, glued and screwed. The LVLs webs were 42mm LVL with 2 crossbands and a 150 by 90 top and bottom cord. Columns were a tongue and groove system, so that the columns were actually wider so that the rafter could slip in between the webs, and the elements were screwed off through there. Base spacings were 15 metres. This was adopted because it gave the best layout for the racking system. We considered 10-metre base, but 15 provided the additional lane between each column system. So, and the structure was 220 metres long, 600 deep box beam purlins. This structure, during its design phase, was compared against steel, and it provided a cost-effective system. So once again, there's the geometry through there. So it was 9 metres high at the eaves. You can see the screw joint through there. So we provided a pattern of type 17 type screws. When it was erected, only a certain number of outer rings of screws were applied to take the dead load of the beams. And then once the was off the hook, and they could come back and finish up the screw rings later. The internal column was the box section, as well as the main roof members and columns. So as you can see, it's a fairly impressive large structure, fairly regular, which makes for size of economy, and the bay spacings are 15 metres, and overall what you see there is 90 metres through there. Internally, you see Nestic through there, where we have LVL mullions and girts in some applications along the building, and construction adopted a prefabbed system whereby every alternative bay was prefabbed on the ground as a modular unit and then lifted up into place to columns, as you can see there, and then slipped into place. So you can see them lifting that middle section through there. Once it was in position, they screwed off a number of rings, the screws, and then the cranes could be released. Thank you very much.
Okay, thanks, Rob. And George, please come back and we'll get into some questions. So I'll moderate this section, and thank you for all a brilliant talk. So we've got about a number of questions there, and we'll start from the first one. And the first one's actually to you, George and Petro. The fastening of the column to the beam connection of the portal seem to be very close to each other. What is the criteria for the minimum distances?
In terms of that, the screws that we're using are the Simpson Strongtype SDWS frame screws. Now they're quite a large washer head screw, so the pictures might look a little bit misleading in terms that the washer head is extremely large compared to the diameter of the screw. So what we've actually used for the spacings there, we've used the recommendations from Simpson Strongtype in their technical literature for a cross grain, a long grain, edge distance and end distance. So if you have a look at the timber portals there, you'll find that a lot of them, the screws are actually offset from the centre of the column because we need to get the end distance of the lintel there to get the screw spacing.
Okay, just continuing the questions down the list. Gerard, and I think it's probably to you again because I mentioned Mybrace. So two questions. First being Mybrace usage with brick veneer walls. How is brickwork over large openings supported?
In that would just be exactly the same as whether there was a Mybrace or a standard timber frame there. So not sure. So I think over large openings, people are just going to use a gal lintel, just an angle bar to support brickwork.
Okay. And the second being, not sure if out of plane perpendicular loads become critical to the Mybrace lintel without applying lateral restraints. I'm not quite sure that's a question or a statement.
In most cases, because we've got a prefabricated composite C section, the out of plane loading on the columns is actually quite good and quite significant. So we've found that even in the special Mybrace that was shown, where we had, that was 4.2 metres high, the highest column, and still the 45mm solid LVL with the double C sections laminated to it acted as a composite section without any need for any lateral restraints out of plane.
Okay, George, more questions for you. From Farhad, bottom tie down of upper level portal frames, tie down to timber floors instead of concrete slab.
Yes, and that was sort of mentioned in the in that special Mybrace as well. So what we do is we actually use an 18 gauge frame screw to tie down. We use the same tie down bracket, but instead of using a concrete screw bolt, we use an 18 gauge frame screw to screw directly into. There's probably a little bit of extra work that needs to go there, is actually what do you screw it into. So if you've got an I-joist floor system, you might need to put an additional block in there, or you might need an LVL rim beam. You just need some way to transfer that load back down to the ground floor frames.
The question is, so that's acting as a pin joint or a moment joint?
That's acting as a pin connection. Yeah, there's a single bracket there, so the base connection is solely a pin connection.
Okay, so just got gravity loads and those sort of things to worry about. All right, another one for you, George. You're popular. You thought you'd get away easy. Is Mybrace available in Tasmania? I assume it was from that example you got?
Yes, yes, it is. Yes, we've got Meyer Timber distributes to Tasmania, so definitely available in Tasmania.
And another one from Ken is deflection criteria used for Mybrace.
Deflection criteria. So what we do is we do under serviceability wind loads. We use a 6 mil maximum deflection. We also do an ultimate wind load check as well, where we allow the wind loads to be a bit higher, but we've got a pretty stringent serviceability criteria as a 6 mils.
Okay, does your software allow you to change that?
Yes.
Okay.
Yeah. Well, when we do the software, we actually, because it's at the moment it's only an internal design tool. If the deflection comes out at 6.1 millimeters, it doesn't mean that we actually fail it. It's a matter of having an overall review of whether we can accept larger deflections depending on where the opening is, what the cladding is. So we look at the building as a whole.
Excellent. Okay, let's direct some questions to Rob because he's sitting there. And there's a question from Michael.
That sounds like a great idea, Andrew.
Okay, not lightly.
All right, one from Michael. Are timber portal frames still look economical in cyclonic areas?
Yes, we've done a number of designs up in the northern part of New Zealand, Queensland, I should say. It's a matter of supply, so it comes down to what's available locally, and Meyer and a number of other suppliers are capable of supplying product up in the Queensland areas through there. Generally, you'll find there'll be obviously larger sections, but yes, it is economical. We've done a number of structures up in that northern part of Australia.
Okay, actually, just extending that question, the key point is using stock standard type sizes. Is that the key thing? So
Yes.
More economies come with what's available in shed, not being fabricated.
Correct, exactly.
Okay, another one for you, Rob, from Lisa. Why are you using screws, not dowels?
Dowels, generally, you can use dowels in those situations where you want a decorative application. It has 40% less capacity than a screw. So with a screw, you get the thread biting in and holding the connection together, whereas a dowel is a loose system. So based on some data that was done in the early 70s, you take the bolt data that we use in our code and reduce it by 40%. So you tend to have a lot less, you need more fixings to do it. We do structures designs where we use dowels, but you need 40% more fixings in there. So, yeah.
Okay, either you can answer this one. Alberto, can portal frames be used in residential up to 5 levels?
Generally, you'll find and that if you do the designs on those elements, you start to get a very large overall sway of the truck. You'll start considering a number of other things in there, earthquake design, as well as lateral wind loads. So if you've got a lift core or some sort of core structure there to take out the lateral load, that's probably going to be more economical. Or if you've got internal walls that you can use as bracing, it'll be more efficient and more cost effective to do that than try and rely on a portal frame system completely. You may use it on a facade, and then you might have a brace wall system 4 or 5 meters back from that. Then you can start to use the bracing walls to take those up.
And what we've done, Andrew, is we've actually done a proposal for some 3-story townhouses walk-ups where the front wall was essentially just glass and voids. And we did a 3-story portal frame similar to the Mybrace structure that went through there. But as Rob was saying, the member sizes are getting very large. You're looking at 400 by 63 LVL columns and lintels just to try and get that stiffness in it. So anything over 3 levels, I probably agree with Rob. You need to try and look at getting some other kind of lateral stability out of lift cores or something like that.
Okay, one from Jane. Recommend fixings for transferring loads into Meyer's portal system, especially when built into walls to avoid extra deflection.
What we normally do with the portal frames, we always try to have the lintel as a raised lintel, so have it directly underneath the top plate. or if we need, if we're running out of space, we actually have it built in so that the top of the lintel is level with the top of the top plate on either side. And then we put infill framing underneath it. So that means transferring the loads. In most cases, we try and have trusses or floor systems or anything connected directly to the lintel of the Mybrace portal, which transfers the loads through there. The other thing that we can do with this Mybrace portal, which sort of came as a very good byproduct, is that we can actually put the lintel into the floor system of a multi-storey building. So there are a lot of townhouses out there where essentially the rear wall is just a full height sliding door, and there's a lot more openings that want to actually be floor to ceiling height openings. So what we can do is we can still put a Mybrace portal around that, but have the lintel section of the Mybrace to be sitting in the floor space and all the floor joists butting into it and bracketed off it, and it becomes a floor bearer plus the lintel of the Mybrace system.
Okay, George, last question for you from Mark. Availability of Mybrace in New Zealand?
We haven't got to New Zealand yet.
So world domination hasn't occurred yet. So you
no, but they won't let us in. That's the only problem.
Okay, all right. That's something for the future. And the last question, is because we're running out of time, I'll leave this one to Rob. Are there other examples of timber frames, including monorails or crane runway beams? From Hassan.
Design examples or actual examples?
Just as examples.
Design examples, I'm not aware of if there's any literature available. The same principles apply for designing steel runway beams or steel gantries. So the same design principles are there. It's just a matter of them substituting materials for timber. So you could have if you need lateral stiffness in your runway beam, so you might use a box section or a teed up section in that sense through there. So, but no, I don't know of any design examples, but there's many examples of, and there's one recently just in Bendigo in Victoria where we've designed a structure for a crane rail. So, yeah.
Okay, great. Well, thank you, George and Rob, for your presentation. And now wrap it up because we're just 1 minute to 12. And I did forget to put the CPD questions onto the chat room, mainly because I didn't have a capacity to do that when I was doing this. But here are the CPD questions. Name 2 mass timber products that can be used in portal frames. I think that's fairly obvious. What application purposes timber portal frame perform in house construction? And Rob, last question for you. What purlins did you use in the Myers shed case study?
Plywood LVL box beams.
Okay, all right, thank you. So just to remind you, the recording of this webinar will be available in 4 weeks' time, and all other recordings from the Wood Solution webinars are available from the Wood Solution website. Just Google webinar, just search webinar in the site. This is a series of webinars on a Thursday. We have it running for each week for 5 weeks, and we just completed the first one. Hope you enjoyed that. Next one is on swimming pool buildings. We'll have school buildings and hotels and domes in the future one, so look out for the advertising of that. But our next one will be on pool buildings, and it's going to be via a case study, and it'll be on the Stromlo Leisure and Aquatic Centre in Canberra, and we have the architect Boom Barnes and Darren Salter from consultants, as well as the supplier, wood suppliers from Rubner and XLAM Solutions. The very next webinar is next Tuesday. This is the Tuesday by Tuesday webinars, every second Tuesday, and that one's on 2nd February. It's demystifying bushfire attack levels assessment. Good luck on presenter Maria on that one. That's a very tricky subject, and I'll be listening quite attentively about how that's done. It's a very tricky subject, so it's an excellent webinar. Just a reminder, the Wood Solution team will be sending out the certificates for this. So there's 3 certificate ones available. Please store the certificate in a safe place because we won't be reissuing it. And talk about the recording of that. And also we'll also be sending out a survey. Please, we respect your comments. So if you have time, please fill them in. So at this point, we're now reached past 12 o'clock, and I'd like to say thank you to the speakers, Rob and George, and particularly thank to the people who attended. We'll see you at the next webinar next Tuesday, or the building series on Thursday.